All right, so guys, with all of that said, let's dig into this. Let me grab my book. This is us wrapping up chapter 14 as we move then into chapter 15. That is the chapter that you have, oh shoot. Oh no, I'm not. Oh my gosh. How did I do that? Oh, did you have them up above there?
No, they were like right in the middle.
Oh, you're kidding me. I'm so sorry. All right, thank you. Yeah, my bad. So guys, we have already summarized chapter 15. By the way, I got the stuff back. How did it go?
It went pretty well.
I heard you did a great job playing it up, that it was more theater.
Yeah.
You realize what that means. You'd be a great AP chemistry teacher. Because, I mean, you understand this. Teaching is 70% theater, right? Yeah. I mean, teachers have the amazing ability to make a bunch of 16-year-olds care about something like chemistry. That's theater. Oh, it is. Yeah. I mean, I think business people have got the easiest jobs on earth because they're trying to sell stuff to people that actually want to buy it, right? Yeah. Ditch your headphone if you would. If you're okay. Yeah, no, you're fine. All right, so guys, questions on the homework as we wrap up chapter 14? 85? Is it hard? Oh, I hope it's not hard. Oh, it looks hard. Okay, what are we doing? Catalyst. Okay, oxidation. Here, did I rewrite the question? Oh, look at me go. Okay, so find a mechanism? Let's see what it says. So it's under the heading of catalyst, so I would be surprised. Oh, it is the first step of verifying a mechanism. So it says oxidation of yada to yada is catalyzed by yada. The reaction proceeds. Oh, so it's telling us this is how it happens, right? So I was reading this like a verify a mechanism, but they're saying this is how it happens. So it says show that the two reactions can be summed to give the overall oxidation. But John, just eyeballing this, do you have it in front of you? So just eyeballing this, what I'm seeing, and this is, I haven't looked at the answer, but I'm seeing NO coming out of the first reaction as a product, and then I see it going into the second reaction as a reactant. So what does that make it? Goes in, comes out, goes in. No, intermediate. Okay, so that's our, and we'll talk about catalyst in a minute. But guys, this isn't a part of the question, I don't think, but let's be clear. Do you see that NO is an intermediate? Because it comes out and then goes back in, and it never shows up in the overall equation. So with that said, you notice that there's two down below and one above, so we probably had to double the first thing. Hey, look at that. Okay, good. And so then, why do we consider NO2 a catalyst and not an intermediate? So guys, it's important to understand the distinction. With an intermediate, it's a product in one step that becomes a reactant in a future step. Catalysts are the opposite. They're a reactant in a step that then becomes a product in a future step. The idea is that they go in and come out unchanged. Now guys, understand there's two ways that can happen. If it's a homogeneous catalyst, they literally are part of the rate law many times. And that's what you're going to find in lab. They are a part of the rate law many times because they go in as a reactant and their concentration can influence the rate of the reaction. And then they just come back out as a product and then they just keep doing their catalyst thing. With a heterogeneous catalyst, right, that's the surface, the Enya stuff. Guys, if you've got a heterogeneous catalyst, it's not considered a reactant or a product. It's a surface that allows the reaction to happen more favorably. So, is that question C? Is this an example of a look at me go. So this would be an example of a homogeneous catalyst because it literally functions as a reactant. Heterogeneous don't, it's just a surface.
It also shows like gas on it.
Oh. That's interesting though, Michael. Could you have a heterogeneous catalyst that's a gas?
Well, they're all gas.
No, I know. I'm just thinking, because, yeah, I know that in our previous definition of homogeneous, it means in the same phase. But really with catalysts, homogeneous means it functions as a reactant in a product. Heterogeneous means it functions as a surface. So my question is, could you have a catalyst that's in the same phase and yet just functions as a surface? Come on, give me an answer. I don't know either. But what I'm trying to be careful of is, can you assume that if all the phases are the same, it's necessarily homogeneous? Probably. I think you're probably safe with that. Anyway, how'd we do? What else, y'all? Good? Man, you're making this easy. Let's get this recorded. How, what? So we haven't quantified it, but we've talked about it. So we know that the more, let me step back a second. We talk about effective collisions, right? And the things, and this is a little bit of what you missed last time as well. We've already said that if we want more collisions to be effective, we want them to hit harder, magnitude, and more often frequency, right? There's another factor that influences collision effectiveness, which is orientation. They've got to hit so that some reactions, it matters how they hit. That's what heterogeneous catalysts do at some level, is they increase the likelihood of effectively oriented collisions. So all of that together gives us that in order for collisions to be effective, they got to hit hard, they got to hit a lot, and they got to hit well aligned. The collision factor is a quantification of those things. Don't worry about it.
Surface area for smaller particles is like, well, it's more than bigger particles because there's more particles to
It depends. The thought, so it's comparative. So if you've got a big chunk, and if you can turn it into smaller chunks, then it would have more surface area. Yeah, that's true. Y'all good? Okay. So I need to pause. And guys, you're gonna need some paper. Restart this. Jump right here. All right, guys, chemical equilibrium. Oh, yeah. Let me get my tubes. Uh-oh. Oh, no. Oh, no, we're good. We are okay. So, we did this last year, right?
Yeah.
The two. John, what was your favorite part of this? Right here. Did you like that one part where we went like this? Was that your favorite part? Just say yes. You loved that part, didn't you? So guys, John gets to have the mystical, magical experience of doing this for the first time. Oh yeah. Imagine if you could, Men in Black style, blank your memory and do this as if you'd never seen it before. Turn on what? No, this sort of hypnotizes on its own because of the clicking sound, right? I find that this is sleep-inducing all on its own.
Have you done this for Jen?
No, this is See, John, again, John gets the full experience. I know. John, we are living vicariously through you. Oh, entropy just went up. No, it's true. So, guys, here's the thing. This is a model. This is an analogy. Let's just call it a model. It's not an analogy. So, guys, this is a model of how chemical equilibrium works. Now, as we talk about models, guys, you understand that models have limits, right? There's only so far that you can go with a model. But guys, here's the thing that's cool. We haven't even begun to push the boundaries of where this model can take us. As a matter of fact, I would propose to you that this model was at some level inappropriate to share with you in general chemistry. Guys, I had to do a whole bunch of fudging in order for this to be okay to share with you in Gen Chem. Guys, now we actually get to not gloss over the other really interesting things that are going on here. But guys, we actually get to talk about them, and that's cool. But in order to do that, we need to pick up where we are right now. But guys, before we do, I'm realizing, could you do me a huge favor? Miss Call needs this more than you know. Would you mind running it to her? Thank you. All right, so guys, maybe you remember, let's talk quickly. Guys, we use this to model equilibrium, right? What is happening at equilibrium? If you were to look at a system at equilibrium, what does it look like happening? Nothing. It's just sitting there. No change. It doesn't look like anything's changing, but guys, we understand full well stuff is changing. Reactants are becoming products. So why does it look like nothing's changing? Products are becoming reactants. Now, guys, let's not dig too deep yet, but when we reach that magic state of equilibrium, we know reactants are becoming products, and products are turning back to reactants. But when that reaches, remember that's called reversible, right? It goes both directions. Ooh. There's a thermochemistry term. Guys, that is a reversible reaction. And so it gets to that magic point where it's going forward and backward at the same speed, but we don't call it speed, we call it rate. If only we had just done an entire chapter about rate. Gosh. And maybe what we could do is we could take all the interesting things that we know about rate and apply it to, Oh no, it's true. Guys, we understand this, right? Schweppes. Guys, we understand the chemical equilibrium occurs when opposing, reversible reactions are occurring at equal rates. Write it down if you need. But guys, that is what that's what this is all about. Would it be distracting if we talked about change? I don't care. We're going to talk about it. So, guys, Gibbs free energy, change in Gibbs free energy, spontaneity, all of that good stuff. So, guys, we've talked about equilibria, and we've talked about it in the context of reversible and irreversible. We've talked about it in the context of spontaneous and non-spontaneous, and we've talked about it in the context of changes in Gibbs free energy. So guys, again, reversible and irreversible, spontaneous and non-spontaneous, and change in delta G. I'm going to actually write these down, but you shouldn't. So, reversible, irreversible, we'll let that be close. Spontaneous, non-spontaneous, and change in delta G. Well, change in G. delta G. Guys, talk about it with the person closest to you. If a system is at equilibrium, what's going on in each of these aspects? Should we send Eleanor over to be your Clara? Here she comes. Clara, we think you might have been replaced by Eleanor. Sad, I know. I'm sorry? I know. I know. This could redefine a lot of relationships. All right, guys, let's talk. So when we have a reaction that is at equilibrium, is it spontaneous? Yes or no? No. But guys, remember, that doesn't mean that nothing's happening. It means that everything's happening. So guys, let's talk then about what spontaneous means. If a reaction is spontaneous, it has a direction that it always goes, the spontaneous direction, and it has a direction that it never goes by itself. That's the non-spontaneous direction. So guys, if you have a reaction that is equilibrium, we do not consider that to be spontaneous, not because nothing's happening, but it doesn't have a direction it does go in a direction it doesn't go. Is that okay? So therefore, and guys, the next one, the reason I skipped it is because we know it's reversible. It goes both directions at the same time. Remember, the tie is that irreversible is spontaneous. But guys, again, don't get the idea that irreversible means can't go the other direction. It simply means doesn't go the other direction on its own. So then, guys, let's talk about delta G. So if a reaction is if a reaction is at equilibrium, what is its delta G value? Big old 0, right? The forward and reverse reactions are happening through the same pathway. We understand pathways now. Happening through the same pathway, forward and reverse are just undoing each other, and there is no change in delta G. Good? Then guys, what if we have a reaction that has, so this is our 0 point, reviewing for the AP test, what if we have a reaction with the negative delta G? It is always spontaneous in the direction written. What if we have a reaction that has a positive delta G? It's spontaneous in the other direction. Huh? Are we good with all those interrelationships? Okay. So guys, with that said then, come on, baby. Go ahead, Mila. Thank you. It doesn't. Apparently, though, somebody said Miss Callsboard's doing this too. I think it may be a driver issue. Sometimes. One time I had a sub that wrote all over my board in permanent marker.
Well, are you serious?
Oh, yeah. And I cleaned it. Does that count as nice? Go ahead.
So, since equilibrium reactions are at equilibrium, I guess equilibrium reactions probably not very word, but when reactions are at equilibrium,
Yes.
the enthalpy and the entropy are probably also equal to 0, right?
No. You don't mean enthalpy and entropy, because there's no such thing as zero entropy. That's absolute 0. So you mean changes in enthalpy and entropy. Okay, so keep going.
Well, I was thinking since, they're going back and forth, if like reactants to products decreased entropy and enthalpy, then products to reactants with decreased entropy, right?
Oh, I see what you're saying. So here's what we know. We know that delta G is equal to delta H minus T delta S. So somehow or another, the forward and reverse changes in enthalpy and the forward and reverse changes in entropy must in some way sum to zero. So I've never thought about it in those, and guys, open this up to all of you. So what Jonah is asking is if we have a reaction that is reversible, its delta G value we understand to be zero, which means that these two terms have got to come together, sum, if we consider the delta S negative. They sum to zero. So does that mean that the delta H and the delta S for the forward and reverse reactions are the same?
Well, because like if you're in an equilibrium system that they weren't both zero, then you have the system increase and become more equilibrium.
Right.
They have well becoming more invert.
Right. That's a good point. Because that's what so if we were to do delta G forward and delta G reverse, we know that those would both be zero, right? I think, Michael, that's the key, is what you're saying is true so long as the temperature's not changing. Because if the temperature were changing, that means that this value would have to change in order to chase this back to zero. So I think you're right. That's a brilliant insight. So long as the temperature's not changing, then yes. But then it becomes an even bigger conversation, because if the temperature is changing, now we're exchanging energy with the surroundings, and one of them is no longer spontaneous because the surroundings is driving the process. So I think the answer is it has to be at a constant temperature, and then the answer to yours is yes, they're the same. I've never ran down that trail before. That's really interesting. Michael, thank you for that. That's a great observation. You guys good on that idea? All right, so guys, here's what we're going to do. So, John, you're going to see that those around you are going to lean into this. Again, it's your first time. Reactants in equilibrium with products. Skip down 2 lines, write it big. If I get food coloring water on my Mr. Ellingford shirt. Yeah. All right, guys. As we said before, this model gets better. There are certainly limitations to it. But guys, this model gets better as we dig into it more deeply. Again, in General Chem, when we did this the first time, guys, Miss Call and I frankly we've probably restructured this day in general chemistry like 4 or 5 times, trying to figure out a way to let this represent equilibrium without creating confusion. So guys, if you were not confused by this last year, it's because we tricked you. So guys, let's do this for real, and let's talk about the stuff that Ms. Call and I have struggled to try to gloss over. So guys, do this if you would, please. You've written this in your notes, right? Above the equilibrium arrow, please write the rate law for the forward reaction. Then guys, below the equilibrium arrow, please write the rate law for the reverse reaction. Go. You guys all set? So you're going to need to edit a little bit because I'm sure that none of you did this exactly right. but let's talk. So guys, it goes like this. Rate forward, we're going to call that rate sub F, is equal to K forward. And guys, when you write that K, please make it lowercase. It's going to matter in about 20 minutes. So K sub forward times what we'll simply call the concentration of the reactants, or reactant in this case. So guys, given that model, doctor up your bottom one. So guys, as you're making modifications, then you should end up with this. Rate reverse is equal to K, that's kind of an R. Guys, is equal to K reverse times the concentration of the products. So, guys, there's some interesting observations that we need to make here. First of all, the reactants for the reverse reaction are the products. Does that make sense? We arbitrarily call them reactants and products, but if we're calling these products, they're actually the reactants for the reverse reaction. Guys, in addition to that, the K value for the forward reaction and the K value for the reverse reaction are not the same. They are not the same values. If you're not exactly sure why, probably the easiest thing to do would be to show you this. So this is the activation energy for the forward reaction. This is the activation energy for the reverse reaction. And if nothing else, we can see in that the K values are going to be different because their activation energies are different. Is that okay? Okay. So guys, with that said, hopefully I can clean up this mess without erasing. Oh, look at that. All right. So guys, with that said, we're now going to do the deal. But guys, you can just stop taking notes. We're going to think. So guys, here we go. Reintroducing you, or John, for the first time. We have reactants. We have products. Then guys, we have blue juice. And guys, the blue juice represents yes. Guys, the blue juice represents the system. Didn't get to say that before, did we? So guys, the blue juice represents the system. But then specifically, the volume of the blue juice is analogous with the concentration of whichever tube that it is in. So guys, tracking numbers, and sadly, we'll see. We'll see. So guys, 100 milliliters, obviously 100 molarity is not a thing, but we're going to say that milliliters are molarity. So guys, where is that represented in the two rate laws that you wrote? What's in the brackets, right? Guys, right now, we have a lot of reactant, high concentration, and right now, we ain't got no product. Huh? Okay, so guys, what does that mean? Well, when this reaction starts, I'm going to try to write on here without making a permanent mess. Guys, when this reaction starts, we have a very, very high concentration of reactant. So what is the rate going to be? High. But then, guys, as the reactant turns into product, what's happening to the amount of reactant? It's going down, and we know that reactions are always slowing down because the concentration of reactant is always going down. We established that at the beginning of this unit. Now you can see it visually. Uh-oh.
Lovely.
I know, right? Guys, as a reaction goes on, by definition, it is consuming reactant. And as it consumes reactant, the concentration of the reactant is always going down, and consequently, the forward reaction is always going down. So now, guys, let's just sort of start here. This will be good enough. So, guys, we know that as this reaction goes on, the amount of reactant is going to go down, so the forward reaction is slowing down. But, guys, as the reaction goes on, what's happening to the concentration of product? It's going up. That's this. And as the concentration of the product goes up, what happens to the rate of the reverse reaction? It speeds up, and eventually what happens? They end up at equilibrium. But now, guys, this is the tricky bit. These K values are not the same. And if the K values are not the same, does it make sense that the concentrations also won't be the same to reach equilibrium? Let's talk more about that. So, guys, last year when we did this with you, we lied. Oh! Guys, we lied to you horribly. And the thing that, not lied, but guys, we were purposefully deceptive. Because to be honest with you, we did not know how to talk with you about these tubes. So we said something like, these are the initial rate. That's not true. You guys know that the initial rate of the forward reaction is at a maximum, and that the reverse reactions rate is at a minimum, 0 initially. So this does not represent the initial rate. But guys, now we can talk about it. What do these tubes represent? Not the reaction orders. They represent K. Guys, these tubes represent the value for K. So, and you understand we're talking these guys, right? So what we're going to say is that the larger diameter tube is our K forward. And guys, before I get too deep into this, I'm going to get rid of my lines. So guys, the larger diameter tube will be our forward K value, and our smaller diameter tube will be our reverse K value. Okay? By the way, guys, from the last unit, what did we find out K depends upon? Temperature, surface area. What about catalyst? Orientation. Guys, what about catalyst? Catalysts do not change the value of K. As a result, they don't change the equilibrium ratio. Guys, catalysts do not, and you guys know where this is headed, right? We've got this thing called Kc, which is the concentration of products divided by the concentration of reactants. Do you guys happen to remember the Kc value for this? It's actually 70 over 30. But guys, and we'll talk more about this later, adding a catalyst to this reaction does not change this ratio. It just gets there quicker. Okay, let me clean up a little more. I know. What's that? I know. So, you know I was a furniture maker, right? Did you know that? Yeah, so in the summers, for a couple of years, right after I used to frame houses, like I was a carpenter, so I used to, between river guide and high school teacher, I framed houses. But then when I got married, my wife's best friend, her husband, was a furniture maker. And so I would go up in the summers and I would build furniture with him. And I learned a lot from him. But one of the things that really stuck with me is never go to the next step until you clean up your mess. I'm like, come on, Chris, what a waste of time. And he's like, no, watch. And sure enough, if we didn't clean up, we were always looking for tools. But if we cleaned up between each step, We always knew where our stuff was. Kind of stuck with me. Anyway, all right. So, guys, this then becomes the idea. You are about to see all of this come to life in a big, big way. So, guys, first of all, this is our concentration of reactant. Jonah, put a name to it.
Hydrogen peroxide.
No.
Antimony.
How much?
Oh, 72.
Butt ton?
Crap ton.
Crap ton. All right. So, guys, we have a crap ton of reactant. What do we call none? How about if we just, can you have negative crap tons?
Crap none.
Crap none. All right. So, guys, here we have a crap ton. Here we have a crap none. But, guys, you ready to do some math? Check this out. We have our forward and our reverse K values. And, guys, these have values. So here we go. We have a K value, but this is times crap none. And what is any number times 0? 0. That means our reverse rate is 0. We have a K value, it's this, but we have no product. Consequently, the reverse rate is 0. Guys, literally, this times 0 is 0. This is doing multiplication for us. But now, guys, this. Now we have a forward K value, but we also have a lot of reactant. So a K value happens to be bigger, but a K value times a high concentration, when we multiply those together, we end up with a very large forward rate as represented by the amount of water in the tube. Literally, guys, the amount of water in this tube is representative of this multiplication. Big concentration times the K value gives us the rate. That's the amount of water that's inside this tube, and it's a lot. Do you get the idea? See how this just gets better? Guys, it's so hard to talk about this when you can't talk about K values, because there's no way to talk about what's really going on here in Gen Chem. We change the way we do it every year, and it's never satisfying, but it gets close. Okay, so guys, here then we go. John? All right. So guys, we understand that when this reaction starts, we have a lot of reactant to turn into product. What does the amount of water here represent? No. The rate. So guys, again, this is important. Concentration, K value. K times concentration gives us rate. Okay? So we have a rapid forward rate, but initially we have 0 reverse rate because we had no product to turn into reactant. But now, guys, watch this. How much water is inside this tube the second time? Less. Do you see that represents the reaction slowing down? Less concentration, less forward rate. But now, guys, our reverse rate is no longer 0. We now have some product to turn back into reactant. And so, guys, this reaction continues. As it does, what is happening to the amount of reactant? It's going down. What is happening to the amount of product? It's going up. What is happening to the forward K value? It's not changing. What's happening to the reverse K value? That's the size of the tubes, right? What's happening to the forward rate? Slowing down. K's not changing, but the concentration's changing, so the rate's changing. What's happening to the reverse rate? It's going up. So guys, eventually, what is going to happen to the concentrations? Will these lock in at 50-50? Because the K values are different, right? They won't lock in at 50-50. So guys, as we continue, the forward rate is still slowing down. The reverse rate is still speeding up. Notice that we've gone past 50-50. There's less reactant than product at equilibrium. Oh, John, sorry, we weren't giving you the full sound. Right. And so, guys, eventually it's going to get to 70-30, and it's not going to change. So, guys, I don't know if it's at 70-30, but let's pretend. So, guys, say that this is at 70-30. It's probably close. But, guys, let's say 70-30 is our equilibrium, and we're there. So, guys, if we're now at equilibrium, what is true about the amount of water moving forward compared to backward? It's the same. What does that actually represent as being the same? The rates. So guys, this is important. At equilibrium, as we've already established, the rates are equal. Yes? But that is not true of concentration. Guys, in this model, what is analogous with concentration? The amount of water where? In the cylinders. And guys, the amount of water in these cylinders is obviously not the same. But what is it? If it's not the same, it is constant. It stops changing. And guys, now do the math. You ready? We have a large K value times a smaller concentration. And that at equilibrium becomes equal to a larger concentration times a smaller K value. Does that make sense? Because guys, we know at equilibrium these rates are equal. So if these are equal, these have got to be equal. And if our K value is bigger forward, then our concentration has got to be smaller, making that equal to our reverse, because here we've got a smaller K value, so we've got to have a bigger concentration of product to go at the same rate in the reverse. Does all of that make sense? You're good on those ideas? Yeah? Okay. So guys, the idea then is this. At equilibrium, we are moving the same amount of water forward and back. That means the rate is equal as represented by these amounts. Ooh. As represented by these amounts. But guys, again, and you were hesitant on this, at equilibrium, the rates are equal. What are the concentrations? Constant. And in this case, that constant is 70-30. So guys, if you want to scratch this down with me, actually, let's do it more formally. Let me see if I can back out of this. Guys, you want to skip down like 4 or 5 lines? Oh, I can't quite get there. But guys, it goes like this. We call this a capital K, because this is new maybe, right? It's not new, but it's been a while. Guys, this is called a K value. But that is not lowercase k. Sadly, this is a capital K. The C stands for concentration. And it is always the concentration of products divided by the concentration of reactants. But guys, we are going to say that that is equal to 70 divided by 30, or 7/3. Now, guys, for most of you, this is going to be lost. For Clara, this is going to breathe life into her soul because she's a little math nerd. Clara, sorry, we're going to do this in your absence, but we're just going to imagine the joy that this brings you sitting at home. Yeah. So, guys, 7/3, right? Does that change? No. So guys, if we do this, if we come along and if we add some reactant, is it at equilibrium? No, because we've got too much reactant. So guys, what is this reaction going to do in response to adding reactant? What's going to happen to the amount of reactant? It's going to go down. What's going to happen to the amount of product? It's going to go back up. When is this going to stop changing? When it gets back to 7/3. But guys, take that idea and apply it to the rate laws that we wrote. Which one of these factors in blue changed when I added reactant? The concentration of reactant. So guys, this changed. That went up. So if that goes up, what happens to the rate of the forward reaction? It goes up. So when we add reactant, it initially accelerates the forward reaction. We see that as more reactant turning into product. So accelerating that forward reaction causes the extra reactant to turn into product until it settles down at equilibrium. But guys, that equilibrium will not be 70 divided by 30 because we've now got more than 100 milliliters, but it'll stay 7/3. Yes? Guys, by the way, that adding reactant or product, or what if I take away reactant? Now what does that do to the reaction? What is our forward rate now if all the reactant's gone? 0. So now our reverse reaction is faster, and it does the same thing. And it ends up back at equilibrium at what? 7/3. Guys, there's a scientific principle for that idea that we can do anything we want to this reaction and it'll always come back to the same equilibrium. Do you remember the name? Le Chatelier's principle. We're going to talk about that in greater detail later. We're going to do a lab on it as well. But guys, those are the fundamentals of Le Chatelier's principle. That whole same side does the opposite side does the same game. Know what I'm talking about? Right? Yeah. But now you know why, because you understand that doing something to a reaction actually speeds up or slows down either the forward or reverse rate. And as they close back in on each other, they come to the same equilibrium. Yeah? So now, guys, the $11,000 question. Why 7/3? What is it that determines 7/3? The K values. Guys, it is the ratio of the K values. It's the sizes of the tubes. All right, Clara, here we go. You ready? What color do you think Clara would appreciate? Well, we need to ask Lynn's because she's closest. Green? Dark or yellow green? Dark green. All right. So guys, let's do a little Clara work. I'm going to do it on the left because it's really the only place I have space. But do this with me. It's worth doing. So guys, we have a reaction that's, I'm going to make it a little thicker. All right. So guys, we have a reaction that's at equilibrium. That means the forward and the reverse rates are equal. Yuppers? Yuppers. But now, guys, if these are equal, all right, here we go, Clara. We're going to derive an equation. If these are equal, do we also agree that these must be equal? So now let's substitute. K forward times the concentration of the reactants is equal to K reverse times the concentration of products. Good so far? Okay, now guys, what we're going to do is this. We're going to solve the green equation for products divided by reactants. So we're going to divide both sides by reactants, and we end up with this. But guys, if we want to solve for products divided by reactants, now we need to divide both sides by K sub R. This then leaves us with an expression. So K sub F divided by K sub R is equal to the concentration of products divided by the concentration of reactants is equal to big K sub C. So you ready for the big tying together thought? For our reaction, our product to concentration, our product to reactant concentration ratio is 7/3. We call that product to reactant ratio Kc. But guys, Kc, our product to reactant ratio, as John said, is determined by our K forward divided by K reverse ratio. So guys, there is something about these glass tubes that are 7-3-ish. Unfortunately, it's not really just the diameter, because that would be surface area, and that's actually a squared relationship. But guys, the 7-3-ish nature of our Kc value is related to a 7-3-ish relationship between these. But guys, the bottom line is this. If your forward ratio, if your forward K value is bigger, your forward product concentration will be smaller. Your product amount will be bigger, keeping the ratios the same. Do you see all those connections? So guys, do this with me. Grab your books. We're not doing the AP reviews anymore for a while. So guys, how deep are we into class? Minutes.
10, 15.
Not including homework grading. How long have we been doing this? Half an hour?
Yeah.
Okay. Open up your books to page 612. Yeah. 613. So guys, on page 613, do you understand that down the right-hand side there are references for equations? Equation 15.1. So guys, equation 15.1 is reactants on the left, products on the right. We just use P's and R's. Then when you go down from there, we've got the rate law for the forward and reverse reactions, just like we wrote on the screen in blue. Then guys, below that, we've got the first of the equations that are in green. We've got the forward rate law equal to the reverse rate law, plugging in the concentrations, the actual numbers. Then guys, solving that, we've got product divided by reactant is equal to K forward minus K reverse is equal to a constant, which we call K sub C. Yeah? Then guys, at the very bottom of this, you'll notice that they actually graph two different things. On the left, let's do the right first. On the right, you've got the reactant in blue. You've got the product in red. Guys, how do I know that the reactant is in blue? Because you start with some and it goes down. Even if you started with some product, it would still be the one that's going down. So guys, what happens to the rates when this reaction reaches equilibrium? That's graph B. What happens to rate? They become the same. Do you see the graphs overlapping each other? Then guys, look at the left. Again, we know that blue is a reactant because it's going down. But guys, what happens to the concentrations? Notice this is time versus concentration. What happens to the concentration at equilibrium? They don't become the same. They don't overlap. What do? They become constant. Do you see that? That blue and red stops changing. because the rates become constant. This could be our 7-to-3 ratio, but guys, looking at equation 15.5, we understand that this ratio in graph A is a function of the K forward and K reverse ratios because we established that on the board. Get it? Guys, do you understand what you just experienced? College. Because guys, in college, you many times will not have professors that will spend now 40 minutes with you mucking around with blue food coloring water and doing all this work with you to talk about all the rich relationships between Kc and product divided by reactant ratios and rate constant ratios, and putting those all together and talking about all the interactions where at equilibrium the rates overlap, they're the same, and at equilibrium the concentrations stop changing and they become flat, and therefore, and all this stuff. Because literally in college they expect you to be able to read from here to here and figure out what took us 40 minutes to do on the board. Right? Yeah. Yeah. All of a sudden, guys, this class has meaning to you, because just wait for that day when you're sitting in Chem 105 and Professor whomever gets up and goes, all right, guys, let's talk about equilibrium, and draws a couple graphs and comes up with these equations, and then they just keep going. So here's what you get to do. You're going to grab a couple cups, and you're going to grab a couple straws, and you're going to invite all your friends over, and you're going to start doing this, and you're going to be a superhero. Because, guys, you understand the concepts behind the math and behind the graphs. What's that? Have you seriously never had a drink and you stick it in your Coke and you stick your thumb on top and then you pull it out and stick it in? Here's the thing. It does work with water. Yes. So, John, the next time you all are, sorry, I'm going to just run with this. The next time you guys are all gathered at home playing periodic, grab yourself a refreshing glass of water and a straw. You're going to see. So, guys, seriously, we have now spent 45 minutes building a really strong foundation for you about equilibrium. And guys, this was not time wasted. We're done. We're not going to do anything else today. You don't have any homework tonight. Your test rewrites are due Wednesday. No. Yeah. Wednesday, right? Didn't we say Wednesday? Oh, we did? Right, but did we say today? I thought we said Wednesday. We'll talk about it later. So, guys, well, here, let's do this. So, gang, there is actually homework obviously associated with this. But all of this homework is actually all about, we'll do a little foreshadowing. Hey, those graphs look familiar. These graphs sort of look familiar. And we're going to start talking about Kc values and Kp values. And we're going to talk about the information contained in K values. That should be capital. And guys, we're going to talk about hetero and homogeneous equilibria, and then something called Q, which can be used in a predictive sense to get us to all of this. So guys, this is actually your homework. If you don't want to work on it tonight, that's fine. But guys, this is actually our homework for you're just going to learn it all from your book, and no, that's college. Yeah, no, we're going over that next time. So guys, this day gets broken in half always, because I always find it's time well spent really doing a deep dive on equilibria, which we just did. So guys, I'm really okay if you don't work on this homework tonight. let's just pause there and let's talk about what we're going to do with these tests.